You guys doing okay? Good? Perfect. I'm good. I'm good. So, weather is actually really good outside. Even this week and late now, the last week was out. So, the last time we talked about this one actually. So, we tried to do some alytic bromination. So alytic bromination simply means you're gonna find the alytic position of the carbon, and you're gonna do the bromo group added on that carbon here. So in this case, do you guys actually watch the Monday? Like, oh, you did. Oh, perfect. Okay. So the alytic position actually is here. So if you have two carbons in the double bond, and you have a neighboring carbon right next to those two carbons. Okay. So you have 2 points here and here. Okay? So alytic position is these 2 points over here. So you can do either these two or these two. The two scenarios, because you have two neighboring carbon here, right? So either you can do this one, okay? Or you can do, because it's the alytic radical resonance, you can do this one. This is the one scenario. Okay, you can either do this one or this one. Okay, by just switching the resonance structure over here, and then you can also do this one, these two. So this can be on here, this, or you can do this. Okay, so you have 4 possible points where you can put the bromo group there. Okay, so if you do this one over here, you can do this one first. This is so these 2 points over here. So it's related where there's 2 points over here, and you can do these two, which will be simply this one. So it will be either moving this one over here, right? Okay, over here. So technically, these are the same because you can just flip it. So you have to have 3 compounds as your product. So this is what we did last time. Okay. I can move on, right? Can I move on? All right. So the next part. Okay. All right. So here's one thing you can also do: making some organohalide compounds. We do using alcohol, using alcohol. So alcohol simply means what? Any compound that has the hydroxy group. So if you have some hydroxy group with any compounds over here, you can call that alcohol because it has a hydroxy group over here. So there's one thing I can tell you is that if you have some hydroxy group over here, you can treat it with some kind of binary acid like hydrogen X. Okay, so hydrogen X simply means you have like HCl. Okay, so you have the halogen, which is chlorine, bound to the hydrogen. It forms the binary acid here. If it does that, it can actually form this one with one. Okay, so what happens to this one is here. This might be something we're gonna discuss in next chapter, and I assume you guys taking over 2 next semester as well, right? So what you can remember this one. Do you see the hydroxy group is actually a very poor leaving group? Okay, so if you try to remove this one and switching it to the halogen groups, you have to make it leave, right? But for now, the this hydroxy group is very strongly bound to the base of your compounds. So we need to do it in this way, because if you do this way, usually they're very strong acid, right? So what that means is what? They're gonna put a lot of this one, okay? They'll be fully dissociated. So if they fully dissociate, if you look at this is what it actually looks like, right? This is what it looks like. There's a 2 lone pair on oxygen because it has what? Group 6 element. So it'd be 1, 2, 3, 4, 5, 6. So you don't see it there, but there's 2 lone pair is implied there. Okay. So what they do is they try to grab the proton. Okay. So they grab the proton, meaning they become water. Pick up the proton here. Water. So in here, there's only 1 lone pair there, right? Then it becomes only 1, 2, 3, 4, 5 instead of 6. So this water group become positively charged. Okay. Then they become better. So they become better leading. Because this is a positive charge oxygen, and there's a pair of electron between this oxygen and this R group here, right? They goes to them. Then they can break. So when they become a positively charged water groups from the hydroxy group, they can finally leave from the base. Okay, makes sense, right? And then once you have this one left, okay, this is the way you have a positive charge, because the oxygen just steals the pair of electron in the bond, right? So this hydrogen go to the negative charge over there. Collaboration. Makes sense, right? Does it make sense? Okay. So, but the thing is, it's not always like this. It's not always like this. This works better when you have a more substitute high degree of the alcohol, meaning you have a methyl alcohol, which is methanol, right? This is the primary, because you have a 1 R group attached to this carbon. You have a secondary alcohol. You have a tertiary. So if you compare this one, I actually put them on the increasing the order of the reactivity. It means this will not be so reactive with the binary acid like HX form, not so much, but tertiary might work very well with this HX form halogenation. Okay? So because the, can you guys actually guess why? Why the reactivity goes up when it's more substituted? Because when they water leave, they become what? Carbocation. Perfect. Excellent. So this will become more stable in the carbocation. This will dominate to leave the water. Then the halogen, negative halogen will come in much easier, much faster. Makes sense, right? Perfect. That's very good. So one example I can give you. Did you copy, right? Copy. So the one example I can give you. I got actually one. Oh yeah, this is okay, and you can treat this one with the HX form. In this case, I'm going to use chlorine, so it'd be hydrochloric acid here. Okay, just some organic solvent. So if you do this one, you're going to have this one. Okay, that works because if you look at this carbon over here. This one has 1, 2, 3 R groups, so it's a tertiary alcohol. So it works well with this binary system. Makes sense, right? Good. All right. Perfect. Yeah, I think you just got this one anyway, but maybe can you guys try this one real quick. You just need to switch one thing. That's it. Okay, just like 1 minute. I think this is quick. Okay, 20 seconds. Okay, so yeah, so you see this one, right? Okay, and when this is positive, negative, it's there. So okay, makes sense, right? All right, so the problem here now is what if we have a primary or secondary alcohol, right? That will be not so effective with this type of a system. So what we can sometimes do is, I'll give you one example. Okay, so if you have this one, okay, if you have this one over here, what you can do is you can use the dionyl chloride, SOCO2, in some pyridine solvent. Okay, pyridine solvent here. So once again, what it does is they try to replace this one to chlorine. So it will be chlorine now. So this is what you can do. This is only what? Secondary on this carbon. So you can do much well with the previous one, but you can use this method here to make it chlorinate. So what it does, actually, we're going to discuss in chapter 11, but I'm going to tell you briefly that once again, this is not a good leaving group, but this will bond to here. And then when it bound this one to the hydroxy group, that makes the better leaving group. And their numbers of the chlorine anion came out when they bound to it because of the shift of the movement of the sequential movement of the electron pair. And then this one bonded. So that's why you have a chlorine instead of hydroxy group after this. And yeah, pyridine will do something. Okay. So I'll just move on. We'll discuss this on chapter 11 anyway. Okay. Let's try to do this one. You have also secondary alcohol, but you want to make now bromination. Okay. So to do that, you cannot do this HBr, will be too slow, right? So we can do phosphorus tribromide ether. And then only thing you have to do is just switch that one to brom group. Right. So it's the same. Again, this will bond to this one, and then when it bonds this one, they release the bromine. Actually, there are three. So they're going to have the phosphorus acid at the end, but I'm not going to go there today. But when it bonds to this one, they become better leaving groups, and there's one bromine will actually get attached to this one when it left together. But we'll do this again in chapter. So this is something we can do, even though you don't have a tertiary alcohol. We can have other method to just halogenate the compound anyway, which will be more heavily discussed in next chapter. Can I move on? Oh yeah, we'll discuss anyway. Okay, next. I think this Friday and next week. And then from there, we're gonna do a lot of review. Okay, so for the fun. Oh. So you have another one we call Grignard reagent. Okay. So Grignard reagent means whenever you have some type of halogenated compounds, like here, you can treat it with some metal. Okay. So this, in this reaction, they treat it with the magnesium metal. Okay. So if you treat this one with the magnesium here, what it does is they actually make this. So this is like a alkyl group bound to the bromine, where you can say what this the bromine group attached to this one. Do you guys remember the nomenclature of this one? Like you can either do two-way, right? Bromo hexane. You can also do what? Hexyl bromide, or either way. So anyway, so this is same as what? This form, right? So any R group, alkyl groups bound to the bromine here. And then a magnesium just get into right between. So when it treated with the metal, they become like X, the halogen, but in this case it's bromine. This one. Okay. So in this case, as you know, this is kind of weird. Do you know why? Because it's metal. So metal, for metal, it's kind of do special things. I guess taking inorganic sometime next. You guys not taking inorganic? Okay. So metal. So this is what we call organometallic compound, because this can be just easily explained by the regular organic chemical way, because the metal, there's kind of hard to explain whether the electrons are really located near metal, but only one thing we can finally for sure is this one. So what is the characteristic of the metal? And what is the characteristic of the halogen? This is a halogen. Any halogen is okay. Mostly chlorine or bromine. This is metal, right? And this is the R group, which is what? Carbon-based. Carbon. Okay? So think about it. Compared to the carbon, the halogen group is what? Much more electronegative. I mean, not so much in the down column, but most of the common halogen is much more electronegative than carbon, right? How about the metal? Metal is much less electronegative because what's the characteristic of the metal? They want to lose electron, right? Because metal, okay? So then, what happens to this one is when they break apart, at this time, the paired electron goes to the carbon. That's what happens. Okay. So I can show you. So if you treat this one, and then maybe you can treat this one here. I can show you. This will become in this form, right? Okay. And then when you treat this one with water, okay, they can actually grab the hydrogen cation. So they just leave like this, and they grab the hydrogen. So they become just a hexane. Because of the carbon has a much more, relatively speaking, stronger force to hold on to the electron, they can use that for making any bond to the other groups, which is, in this case, is water, so they can grab the hydrogen cation. Yeah. So this is Grignard reaction. I'll just move on today, but this will be, I think this will be more heavily discussed in over 2. I'm pretty sure. But I still want you to know what they are, though. Okay. So the next one is what we call Gierman reagent. We're going to use some diorgano copper. Diorganic copper. usually with the lithium. So we call this lithium diorganic copper. Okay. So what you can do is if you have a like a R with the lithium, like a lithium, methyl lithium sort of thing. If there's two, you can treat with the copper iodide, and then what it forms is they can have. There's a two. That's why they're gonna form two R groups. Two R groups attached to the copper, and this is negative charge, and the lithium will be positive charge, making some diorganic copper salt. Okay, and then this will become as lithium iodide. So what is so special about this one is you can actually make the addition of the alkyl groups. So I can give you one example. This is too long, I guess. But so whenever you have this one over here, I'm gonna start from here. Okay. You can treat it with some. You can do that with the. Like the halogenated compounds over here. Okay. And then what you really need to do is you actually going to have this two. So this is in form of R2, copper and lithium over here, right? And there is a two, right? But just choose one. So in this case, it will be just one methyl group over here. And then only thing you have to do is just remove the halogen groups and attach that one R group. That's it. Okay. So what happens is because of this lithium is a positive charge, this is negative charge. There's two methyl groups is bound to this copper here. So the copper, when you bond to here, the halogen group leave, and then that bond to the copper move on to one of the R group. So you're only going to get one R from out of these two bond to copper, and they leave. Okay, does it make sense? So the basic the basic trick you can do is whatever the halogenated compound, just remove the halogen groups and attach the one R out of two where you had the carbon. So let's do one more. Okay, let's do one more. I have one more. There's the iodobenzene. Okay, we have iodobenzene here. Let's say we tried it with this same thing again. Okay, and then maybe can you guess this one real quick? It's actually a pretty simple trick you can do. It's about 1 or 2 minutes. Okay. And what? Yeah, perfect. Yes. That's it. Yeah. So technically, you don't have to know the mechanism, but this is what happens to the compound. Just remove your halogen group and just get one methyl group, and that's your product. Makes sense, right? Yeah, perfect. All right. Maybe can you do just one more, and we'll move on. And oh, maybe I can change this one too. So now it's ethyl group, not methyl. Okay, just the way you see the hydrogen group, remove it, and on that carbon, attach the one R group on your diagonal copper.
So that's CH3CH2.
Mm-hmm.
Okay.
See, it's N2.
Okay.
Yeah. Okay. Pretty simple, right? So just try to get the this one right and remove it. I'm gonna get just one ethyl group, so it'll be this. All right. Makes sense, right? I think I can move on. Okay. Good. All right. So this is the last part of the chapter 10. So the last part of chapter 10 is about the oxidation and the reduction. Okay. So we already learned about this one in Jenkins 1, and I think Jenkins 2, maybe Jenkins 1. So oxidation is what? The loss of electrons. Okay, loss of electron. The reduction means what? The gain of the electrons here. So in this organic chemistry, we kind of looking as more specifically on the elements that bound to the carbon. So what you need to look at is if you have some organic compounds there, for example, you have some like oxygen, where the bromine were here, that makes some change in the oxidative status of the compounds, because we're actually looking at from the view of the carbon. Okay? So what we mean by oxidation and reduction of the compounds in organic chemistry is all for the carbon. So whenever you talk about the reduction or oxidation, we're not looking at those two. We're looking at those carbons. Okay? This is the start point. If you don't get this one, it will be very confusing, because obviously if something is being oxidized, the other one has to be reduced. It's always happen at the same time. But if you have a compound either reduced, oxidated, means it's actually for the carbon. That's why we're saying it's oxidation reduction. Because there's in terms of this one, there's actually no change in overall oxidation status. But for carbon, there is one, because compared to the other one. Okay. So one thing you can remember is if you have a carbon bound to oxygen or nitrogen or the halogen, which is a very good example of oxidation. So once again, I'm talking about the carbon. Okay? I'm talking of the carbon. So for carbon point of view, it has now bound to the very electronegative elements, which is oxygen, nitrogen, and halogen too. So what happens to here, this is where you have common valence electrons still shared together, which is covalent bond. But because of the elements is so electronegative, they have actually a lot of force to pulling their, well, meaning they have a higher chance to find the electron nearby those, meaning electron cloud, electron density wise, is more rich. But relatively speaking, they're not like equally shared on this section. Carbon become, relatively speaking, electron poor, electron density poor. So meaning what? This is being kind of losing the electron density to the electronegative groups there, right? So meaning your compound, when your compound bound to the oxygen, nitrogen, or halogen, you can say your compound is oxidized because it's the carbon. Okay. So technically, it means what? For their point of view, they are reduced because there's the one taking the electron from the carbon. Okay. But for always your compounds, the organic compounds are mainly carbon, right? So that's what we're saying is actually oxidized. So the carbon is actually not so electronegative. There are not many things you can do with the reduction then. But the one good example is actually hydrogen. So hydrogen is still lower in electronegativity than carbon. So if hydrogen bound to the carbon, meaning actually carbon is now stronger. So the lot of electron density from these two will be more toward to the carbon. Huh? Oh. Someone, okay. So so carbon here now have a more electron like a reach, relatively speaking, of course, because it's a bit lower than carbon electronegativity. So in this case, when then carbon is bound to the hydrogen, you can say your compound is reduced because the carbon is reduced. So hydrogenation hydrogenation is always a good example of reduction. So you try to halogenate the, I keep saying hydrogenate the alkene or alkyne, which is a very good example of reduction. Because you kind of surrounding the carbon with more number of hydrogen, meaning those carbon will appreciate more electron density coming from the hydrogens. Okay. So just one more thing. Does it make sense? So good. So if we have the other way, so if those bond to those reduction, oxidation, when carbon bond to the hydrogen is the reduction. So in the opposite way, when you break it, right? When you break it, it means actually what? It's a reduction. So your carbon bound to the electronegative elements, but if you break the bond, carbon now restore the electron density, right? Because they left. Then the carbon will become reduced. So when you break those bonds, it's a reduction. When you make those bonds, it's oxidation. So same thing goes here. When carbon hydrogenated, it's a reduction. When you remove the hydrogen from the carbon, it will be what? Oxidation. So this is the other way. Because either you're forming the bond, breaking the bond. That's the job. Okay? Okay, so I'll just give you one example, okay, and I'll finish too. Okay. So if you have this one, okay, and you have this one, okay, let's make it a little bit longer. You have this one, with this one, okay. So obviously for me, I don't even have to look at it. This has what? The carbon right here, but it actually have a double bond to the oxygen, which is the carbonyl groups. So this is very, very well oxidized in this carbon here, right? So this is very oxidized, okay? Because there's carbon but making even strong double bond with the oxygen. So there will be even more drawn of the electron density to the oxygen, right? So those carbons are very, relatively speaking, quite electron poor because of this very strong bond on the oxygen. Okay. So obviously this one will be very well saturated with the hydrogen, right? This is alkane. So this is well reduced, right? It's very reduced form. So oxidation level-wise, this is the highest. This will be the lowest one. So the topical is these two. Okay, so topical will be these two, right? So if you look at this one here, it's not fully saturated with the hydrogen. Meaning, when you have a double bond, you have to lose 2 hydrogen, right? So they're only going to be 3. How many over here? Okay. So the carbon 1, 2, 3. 1, perfect. Yes. Okay. So in total, you have 8 hydrogen over here. Okay. This is 8 hydrogen over here. And for this one, you have 3. There's 1, 2, 3 over here, right? Okay. So it'd be 3, 3, 6, 7, 8, 9, 10 over here, right? Okay. 1, 2, 3, 4, 5, 6, 7, 9, 10. Okay. But this carbon here is bound to the oxygen here. So this is also not fully saturated, but this one oxygen will take it away. So This is kind of tough call, but we can assume they have a similar oxidation level. So we can put it as like a tie. But the bottom line here is whenever you see the unsaturated compounds or those bound to the electronegative groups, like oxygen, nitrogen, or halogen groups, either if it's bound to more numbers of it or a bit stronger, that makes more oxidized. But if it's fully saturated without any electronegative elements on the compound, it's very fully reduced. Okay? This won't be on the exam, but I just wanted to tell you. Okay, so the bottom line here, once again, when carbon bond to the electronegative groups, meaning it's oxidized. When it bond to the hydrogen, it's reduced. If you break it, it's the other way. That makes sense though, right? The last one. Okay. So that's it for today. Let's do extra credit. Okay.